13th year of Conversations with a Scientist, and we have lots of people to thank, not only our science department, but also the Dryden Youth Opportunity Fund. They have been gracious enough to provide us with a grant, and we appreciate that. I want to remind everybody where the exits are. There's the 2 exits in the back, as well as up to the right and the left as well of these back doors, if we need to do that. And then if you could, check your devices and please make sure that those are all put on mute. And if you have flashing lights, turn those off and all that stuff. And I am going to, and I appreciate everybody who showed up. I know it's a busy week with all the senior night for the volleyball, and we've got a lot of sectional games in the varsity teams. So those of you that fitted in, it's wonderful to see you all, and thanks for supporting us. At this point, I'm going to introduce Nick Muldoon, and he's going to come up and introduce our speaker for the evening.
Dr. Bruce Munger received his PhD in oceanography from the University of Hawaii Manoa in 1993 and has held a senior researcher and more recently a senior lecturer position in the Department of Earth and Atmospheric Sciences at Cornell University since 1997. His research centers on the use of satellite observations to study how natural variability in ocean dynamics impacts marine ecosystems at ocean, basin, and global scales. Bruce teaches the most popular course at Cornell University, Introductory Oceanography, with an attendance that has grown to nearly 1,000 students. A major theme the course centers around is environmental threats to the ocean and the importance of citizen activism to pressure leaders to act now to make a more sustainable world that is fair to future generations. This course was featured as part of a New York Times article on interesting courses in the United States. Please welcome Dr. Bruce Munger.
Well, there's a lot to tell you guys. If anybody can stay after, I'll tell you how I became an oceanographer, which started as growing up in the Pacific Northwest on Puget Sound, logger for 2 years, a lumberjack, and then I had a big decision to make. I realized I was in charge of everything, that I could choose whatever I wanted to choose, and I went back and forth for a year of, do I buy a bigger motorcycle and travel the country, or go to college, which my parents never did, and become an oceanographer to see the world. And so back and forth for a year, and I finally decided to become an oceanographer, and here I am. So anyway, there's more details, and if you're interested in that story, stay after and talk to you some more. Yeah, so I want to talk about climate change, and that's going to be kind of a broad topic today. Oops, sorry, turn this on. So increasing carbon dioxide in the atmosphere, it has 2 big effects on the ocean. One, on the planet in general, that warms the planet, which warms the ocean, which raises sea levels and causes lots of other problems. And the other problem with rising CO2 is ocean acidification. How many people have heard of the term ocean acidification? A few people. So that one, some people think it might be even more bad for the ocean than in the near term, in the next several decades, than global warming. And then a few other, just a couple of slides, just to really scare you and give you the gravity of the problem that we face. And then I want to end it on your civic duty to raise your voice. And my class is popular at Cornell, I think, in part because at the end of the semester, when I've gone through how the ocean works and all that, and then all the threats to the ocean, which are a wide range that I don't have time to talk about tonight, but they include global warming, ocean acidification, overfishing, coastal pollution. And at the end, I asked students, what are you going to do about this? I just informed you. You may not know as much as a PhD in oceanography, but you now know way more than 99.9% of the people in this country. And you have a civic duty to raise your voice, your informed voice. This country runs on an informed citizenry. And in my class, they have an assignment at the end of the semester to write a letter to Congress about a concern they have about a threat to the ocean. It can be whatever they want to write about. It's wide open. You could say, drill, baby, drill, if that's what you feel. Or you could say, guys, we're in big trouble. We need to do something. And I want you guys, you're supposed to be my leader, you know, in Washington. I want you to start acting on these things because they're a big problem. So wide open, and I call it giving students ownership of what they've learned. Instead of just memorizing facts and numbers and walking out and forgetting about it, they kind of look at themselves and say, you know, I can actually do something with this. I'm not an ocean person, and I'm a non-science major, but I now see the big picture, and I feel like I can maybe change the world by asking leaders to act on some of these problems that I'll talk about tonight. So that's the last part. So that's the full. We're done with the lecture. So starting off with connection between atmospheric increases in atmospheric CO2 and global warming. So basic observations. We've dumped a lot of CO2 into the atmosphere since the industrial era. And this graph, there's a lot of information on this graph, but so we're now, how many people know we're at 400 parts per million? So parts per million is a measurement of the concentration of carbon dioxide in the atmosphere, and we've gone from about 280 parts per million to 400 parts per million, a 40% increase in the concentration of CO2 in the atmosphere. And a point I really want to make that tonight, I guess one of the big points tonight is this global warming issue is not an issue of 100 years from now there might be a problem, or 200 years from now there might be a problem. This is a problem that's changing very rapidly now. It took us, you might have thought, well, it took since the start of the industrial era to get into this problem. We must have 150 years to get out of this problem, but this problem is exponential. And since 1980, we've put as much carbon dioxide in the atmosphere since 1980 than we have since the start of the Industrial Revolution. So it's a rapidly changing concentration of CO2 in the atmosphere. And the number, there's like two numbers I want you guys to take home tonight. One is 2 degrees C, that's what internationally agreed upon safe warming. We don't want to warm relative to pre-industrial temperatures on Earth. We don't want to warm past 2 degrees. And that's thought to be able to keep us safe, relatively safe, humanity relatively safe. The other one is that we're rising, the concentration of CO2 in the atmosphere is rising by 2 to 3 parts per million every year. So this thing is not a static thing. In 20 years, it'll be at 450 parts per million. And in my class, every year, I have to change my slide, and I have to put, next year I'll have to put 403. And when I first started teaching oceanography about 7 years ago, they had to memorize that it was currently at 380 parts per million. And now I have to tell my class to remember 400 parts per million. So it's changed by 20 in just 7 or 8 years. So it's a fast-moving change that I want you to appreciate. Quick, the greenhouse gas effect. I really like the analogy of the car and rolling up the windows on the car. So the glass, like a greenhouse gas, the glass lets the short wave, so sunlight is short wavelength electromagnetic radiation, and then infrared radiation is long wavelength. So make the distinction between short and long wavelengths of radiation. Sun comes down as short wavelengths. The glass could care less about short wavelength radiation. It comes right through the window. That's why you can see the stars through the glass. That's why you can see the sun through the glass, because the light comes right through the glass. It hits the seat. The seat absorbs some of that radiation, and when you absorb radiation, you get warmer. And when you get warmer, you re-radiate that energy you absorbed as long wavelength radiation. And the glass, unlike the short wave, the glass lets the short through, but it won't let the long wavelengths out through the glass. And so the car heats. You have more energy from sunlight coming in than you have thermal energy coming out. And when you have an energy imbalance, the car warms. We all know that. We roll the windows up on a warm day, and the car will get warmer, warmer, and warmer. And the car will keep getting warm, slowly but surely, until the glass itself, the interior of the car and the glass itself is as warm as it needs to be for the outside of the glass to radiate the heat out at the same rate at which the heat is coming in. Then it's back into energy balance, and the car levels out, the temperature of the car levels out at that time. So that's the greenhouse effect. Carbon dioxide does the same thing. It's like rolling the windows up. The same amount of sunlight comes through the carbon dioxide enriched atmosphere, just like it did before, no difference at all. But when it hits the Earth and warms the Earth, the long wavelength radiation's being trapped by the increasing concentration of CO2. It's like we rolled the windows up. So we now have an energy imbalance. We've rolled the windows up, and we're starting to warm. And we're warming, the heat imbalance is about 2 watts per meter squared. So the entire planet, there's 2 watts per meter squared coming down to the Earth every single minute, every single day, every single week, every single year. And with more energy coming in than we have going out, we warm the planet. The planet's warmed by 0.85 degrees centigrade so far since the pre-industrial values. And here's that all-important point I want you to take home. 2 degrees. You're going to hear a lot in the news, especially the end of November, 1st of December. There's a big climate conference in Paris. How many people have heard about this climate conference in Paris? So these are attempts. I would call these talks potentially the most important talks in human history. I feel that strongly about it, because you'll see by the end of this lecture, we're in deep trouble, guys, and it's got to get changed right away. It can't be changed 100 years from now. And while the negotiations in Paris and the pledges that have been made are not enough to keep us below 2, that's a first big step to getting us to try to control ourselves, to be not crossing the 2-degree mark. So 2-degree warming above pre-industrial levels, that is the international agreed upon safe level not to cross. 2 degrees is a guess at safe level. It's not a certainty. And we now know, I mean, we're at 0.85 warming now, and we have droughts, we have wildfires, we have hurricanes and floods. So you know, 0.85 is not particularly awesome. We already know that. So 2 degrees is going to be certainly not fun, but at least, yeah, people believe that human civilizations aren't going to fall apart. Above that, we're not quite so sure. And here's a number, I told you 2 numbers, but how about 3? which is 4 degrees C. So, you know, we've gone through a lot of ice ages, you know, where we've had, you know, ice and not ice, glacial, interglacial. 15,000 years ago, we were 4 degrees colder than we are today, 4 degrees. And we had a kilometer of ice on our head. So people might think, what's the big deal about 2 degrees? You're such a crazy person, you know, like 2 degrees. It was 2 degrees warmer yesterday than today. You're a crazy person. And I'm like, 2 degrees, you know, gets, you know, in weather terms, 2 degrees gets balanced by a 2-degree warm, a 2-degree cold. This is a 2-degree year by year by year by year. The difference between an ice age and not an ice age is 4 degrees C. So that was 4 degrees colder, and we had a kilometer of ice on top of Ithaca, New York. So that's pretty like civilization disrupting, right? Like a kilometer of ice. We wouldn't really have the same kind of civilization that we have today with 4 kilometers of ice. So take 4 degrees cold and a kilometer of ice, and imagine, and I don't know what it's going to look like, but 4 degrees above pre-industrial is going to be as awful, you know, civilization-wise, as 4 degrees and a kilometer of ice on our head. So 4 degrees would be super bad, as bad as a kilometer of ice on our head, okay, in the other direction. The Arctic is warmed a lot faster than the lower latitudes, mainly because we've lost snow cover, and that's albedo. The white snow reflects short wavelengths right back through the sky, just like they came in. We've lost a lot of snow cover, and so the Arctic is warming twice as fast as the lower latitudes, and we're seeing a lot of really dramatic changes in the Arctic. Relative, this is just putting things in context of kind of natural variability in the concentration of CO2 in the atmosphere. So for 800,000 years, we've had this heartbeat of the Earth, glacial, interglacial, glacial, interglacial, and that corresponded to CO2 concentrations going somewhere between 180 parts per million to 280 parts per million. So it was like a heartbeat, 180, 280, 180, 280, 180, 280, 180, 280, 180, 280. I used to make my students, this was like 7 years ago for the exam, they had to remember 180, 280, 380, 180, 280, 380. That was like, guys, that's easy. You should be able to remember that for an exam. It's like a sing-song, 180, 280, 380. And now they have to memorize 180, 280, 400. You know, like really dissonant, you know. So that was like 7 years ago, guy, 180, 280, 380. And now we have to sing 180, 280, 400. That's how fast this thing is changing. So this is CO2, 180, 280, 180, 280 parts per million. And then going up and down with that are global average temperatures. Somewhere about 4 degrees C, as I mentioned before. There's ice age, not an ice age, not an ice age. et cetera, et cetera. And then sea level went up something like up and down by about 100 meters. When you go up and you get warm, the planet gets warm, you melt the ice off of Greenland and Antarctica, and you raise sea level. And then when you cool back down, you form more ice on Greenland and Antarctica, and you lower the sea level when you make ice from the ocean water. So when you warm the planet, when you add CO2, you warm the planet, and you raise the ocean sea level by 100 meters. Okay, so natural climate forcings are small compared to human forcings. So the biggest natural forcer that you saw in those last things, there's a lot of things that force climate variability, but the biggest one is those concentration of carbon dioxide in the atmosphere. And then these numbers, this is the global carbon cycle. And we have carbon dioxide stored, or carbon, what I call mobile reservoirs. There's a lot of carbon tied up in carbonate rocks and things like that, really a lot. But mobile reservoirs that you could quickly move from one reservoir to another. The biggest one by far is the deep ocean. So there's 730 units. It's gigatons of carbon dioxide in the atmosphere, 780. There's 38,000 gigatons in the deep ocean. So the deep ocean has, if you brought all the deep ocean water up to the surface in contact with the atmosphere, it would be like popping the can on a Coke. You know, you would have the CO2 coming out of the ocean and into the atmosphere because it's much more highly concentrated down here than it is in the atmosphere. And then land has, quite a bit, but the big ocean is the big reservoir, the big mobile reservoir. The thought is that the thought about the geologic time scale, 800,000 year, 180, 280, 180, 280, is that at those kind of time scales, you pull carbon dioxide out of the atmosphere, bring it up to 280, and then some point later, you pull that carbon dioxide back into the deep ocean, and it drops back down to 180. So it's the transfer from atmosphere to bring it up, and then another transfer back into the ocean. And so changes in ocean circulation are thought to promote the uptake of that carbon dioxide or that release of that carbon dioxide. And it's still not understood very well at all on how that works. But that's the only large reservoir, so it's the most logical place to look for what's the source of the rise to 280 and then the pull down to 180. And it's thought to be these two reservoirs exchange over those timescales. The timing of the ups and downs, it's definitely known to be timed to orbital variations in the Earth around the Sun and the tilt of the Earth around the Sun. And we have small variations in how elliptic the orbit is around 10,000 year timescales or so. It goes from sort of circular to more elliptical. The tilt of the Earth precesses somewhat on its axis, and then the direction of the tilt, summer versus winter, also varies. You sum all those up, and you get something that varies roughly on these time scales. They're called Milankovitch forcings. These are not changing the watts per meter squared of the energy coming into the Earth very much at all. Really tiny changes. So the orbital forcing is quote unquote the trigger that moves the carbon dioxide out of the deep ocean and it builds it up to 280 or so in the atmosphere. And I want to emphasize that. So orbital variations pull carbon dioxide, cause ocean circulation changes that are not well understood, that drive CO2 out of the ocean into the atmosphere to raise the atmosphere level, and then pull, some years later, pull it back down, up, down, up, down. And we are now here, and I now claim that we are now, humans are now the trigger. So it used to be orbital forcings caused the CO2 to rise and cause the CO2 to drop. Humans are now drilling the carbon out of the deep, sediments, and burning it as oil. And we've taken over basically the climate system. We've now raised carbon dioxide levels to 400. Humans are now the biggest trigger. We're bigger than orbital forcing. And James Hansen is probably the world's most famous climate scientist. And he wrote a book 5 or 6 years ago called Storms of My Grandchildren, the Coming Disaster of Global Warming, something like that. And there's a lot of really great stuff in that. One statement he made that just really sank in for me. And he said, humans become so powerful in our ability to put greenhouse gases in the atmosphere so efficiently that we will never, this is the statement, we will never, as long as there's a functioning human civilization that isn't like in caves because we've ruined everything, we will never ever have another ice age, ever. As long as we have a civilization to stop it, we are more powerful I mean, this is all that global, this is orbital variations, like, it's astronomical forcings. The best that they could do is pull the concentration of CO2 up to 280. Humans, we just like flipped the switch and dropped it up to 400, So we are more powerful, humanity is now more powerful than orbital forcing. That's how populated we've become, humans on this planet, and how technologically advanced we've become. We can stop all the ice ages. We never, ever have to worry about an ice age. We can stop it in no time at all. There's other natural variability, solar cycles, volcanoes go off. These are short-term, 15-year, or this might be a 2 or 3 year cooling of the planet. There's also lots of natural climate oscillations in the ocean and atmosphere that I won't talk about tonight, but we've all heard about El Nino. And I'll say El Nino a little bit. So how many people know we have a big El Nino now developing? So El Nino can temporarily, for a year or so, warm the planet, and then a La Nina would temporarily cool the planet. But there are other climate oscillations between the ocean and the atmosphere and the exchange of heat between the ocean and the atmosphere that are called, it can be on decadal scales. So that those can also add to the temporary warming and cooling of the planet. Let's see. So this is basically the sum of all natural variability at kind of 100,000 year time scales, with CO2 being released from the deep ocean being the main forcing, and solar variability and natural climate oscillations like El Nino being relatively small compared to these things. This one, I almost threw this out tonight, but these are on like decadal time scales, human time scales of like since the Industrial Revolution. These bars are supposed to be the strength of the forcing or the cooling, and anything above that graph is watts per meter squared forcing of a warmer Earth, and then these are things that would cool the Earth. And sulfates from smokestack pollution can block the sun coming in, and it can cool the Earth a little bit. But I hope you can see that the greenhouse gases, CO2 being the biggest one, methane and nitrous oxide, these guys stand out as the biggest climate forcers on our kind of time scales of 100 years or so. So this is like, people have heard a lot in the news about humans are largely responsible. Nobody disputes that we are warming, that the planet is warming. And there's a tiny, tiny fraction of people who question whether or not humans have caused it. It's like 3% or less. And you'll see in a minute it's even worse than that. I mean, better than that, however you want to look at it. So the reason, the fingerprint or the evidence that points to humans is kind of what I would call repeated numerical experiments. And people have built climate models, and then they've run those climate models with known natural forces. So this black line right here that you can sort of see the solid line, that is the observed global average temperatures. And the blue line is if you run your model and you don't put carbon dioxide in the atmosphere, and you run the model with all the known natural forcings, you get sort of, since the industrial era, you get relatively, pretty much a flat line. You don't get any global warming. And if you add the CO2 that humans have put in the atmosphere, you get the warming that we've observed to have happened. So I often tell students at this point, like when I was doing experiments in the lab, and I had this great hypothesis that I thought was super cool, and I ran an experiment, and it worked, The joke in the lab would be like, don't run it again, like don't replicate it, because you don't want to, it worked the way you hoped, and now you can write the paper, and obviously that's not how good science is done. Good science is done by repeating the experiment many times over to make sure it wasn't a fluke that you got your result that you got. So this is not one single climate model that one group made and got it to look like humans made this. This is people in Germany built their models, people in the United States built their models, people in Japan, China, Great Britain, Italy, all these separate groups have built climate models, and every one of them, if they don't add CO2, they get a flat line. If they add CO2, they get warming. And it's this repeated experimentation with numerical models that constantly point to the fact that we need human-added CO2 before we get the models to match the observations of the warming. So that is the fingerprint. The IPCC report that came out, the fifth assessment report came out about 3 years ago, stated that, and this is, so how many people know the IPCC, the Intergovernmental Panel on Climate Change, United Nations? So it's like, a couple of thousand of the world's, best scientists. They don't do science, they review the published literature, the scientific literature, and they summarize the current state of knowledge for the last 5 years. What's the new ideas that have come out and got published in scientific journals? They assemble that, synthesize it, and summarize it for policymakers. And each year, every 5 years, they put out a new report, and the last one came out, the fifth one came out about 3 or 4 years ago. It states that, given all the consensus in the scientific literature, it's unambiguous that the planet's warming. Nobody questions that. And then this one, it is extremely likely, and that's 95% likely that it's human-caused, and that's from these repeated experiments over and over and over again. 95%, how many people do statistics and do science, where they have to test a hypothesis? Well, 95% is the gold standard, right? Well, you hit 95 and you're done. You don't have to go any more than that. So, and anecdotally, we are now more certain of human-caused global warming than we are that smoking causes cancer. You can take that one. I'll add one more that's not on here, but which will hopefully just really sort of stop anybody who thinks that this isn't real. It's National Academy of Sciences, every major nation has one, and it's like, I will never be one, a member of the National Academy of Sciences. It's like the Nobel laureates kind of, a club of the smartest people in the country. Every National Academy of Science of every single major nation, 100%, not 97, not 85, not 70, 100%. Every National Academy of Science of every nation on this planet, major nation, has written a letter stating that humans are largely responsible for the observed global warming. So it is it's just so not like, the science is done, the question is, what are we going to do about it? So so what are the consequences of this warming? Sea level rise. The fourth assessment report said, don't worry too much. At the end of the century, sea level will be 40 centimeters higher than it was before the start of the Industrial Revolution. It'll be a small problem, but it won't be a huge one. By the way, I'll just stop there. This IPCC report, it goes through all the scientific synthesis, and then there's one last filter. It goes through policymakers, these kind of government wonks, and they take out they tamp down any sort of exaggeration, and you can be almost certain that if the IPCC says something kind of scary, it's probably even scarier than that. They're the most conservative in cautious kind of report that you could probably ever hope to get. And I strongly recommend you read some of these IPCC reports that come out. There's a policy report summary for policymakers that's super condensed, and then there are thicker volumes that are much more wonkish for scientists that they can read about, climate change with regard to the ocean, with regard to food and food production, et cetera, economies, things like that. So the fifth one that came out, they upped it to 1 meter. Now they think it's going to be 1 meter by the end of the century. That was 3 or 4 years ago. And then this report just came out, NASA scientists. This is now since that last report, so we've had a few more years to add a little bit more data. And then they now think, I think we're going to have to up that. We thought maybe 1 meter, but it could be a little bit higher. Who knows where they're going to come up. I can almost assure you that the sixth assessment report is not going to be 1 meter. It's going to be something greater than 1 meter above pre-industrial levels. So that's sea level rise. This is, by the way, because this would take 1,000 years for all the ice to melt off of Iceland, off of Greenland and Antarctica. But if it ever did, and it could, not in your lifetime for sure, absolutely, 100%. But if it does, it would raise sea levels. Greenland would raise sea level by 20 feet, and Antarctica would raise it by 200 feet, so taller than the sea level rise. Again, 1,000 years or more for all that to happen. Vulnerabilities. Some places are more vulnerable than others. When sea level rises, it doesn't rise equally everywhere on the planet all at once. And these colors aren't the best on the projector here, but the blues are, sea level's actually dropping where it's blue, and where it's orange and red, it's rising. And so the East Coast, it turns out, the West Coast is kind of lucky. The West Coast, sea level's actually dropping right now anyhow, a little bit. And sea level's rising along the East Coast, and it's rising in the Gulf of Mexico. And so vulnerabilities, New Orleans is we all know this now from Katrina, that New Orleans is barely off sea level. Cape Canaveral in Miami down here, Norfolk, Virginia. So, there was a great interview. There was a a senator who's a climate skeptic senator, U.S. senator, and he's in charge of the budgeting for NASA, and he made the NASA director of NASA, the director of NASA, come into Washington, D.C. and sit in front of him with his panel. And this guy's like, so I think NASA's lost its way, you know. Why are you guys, because I'm a NASA, I use satellites to look at the ocean and study the ocean, right? So I know these things pretty well. So NASA's got a great effort to try to use all of its technology to orbit Earth and to look at, it's called Mission to Planet Earth, or it was used to be called that. And it's to use all of NASA's technology to look at what's happening to this planet at planetary scales, because we're affecting the planet at those large scales now as human beings. Anyway, the senator's like, I think you've lost your way and your vision, you know. You shouldn't be looking at Earth, you know, like, don't look here, you know. He's like, you should go, like, off to Pluto or something like that, you know. We're trying to tell him that NASA shouldn't focus all of its attention on climate change issues because he doesn't believe in it, I guess. And the response of the NASA director was, well, sir, we can't launch rockets to Pluto if Cape Canaveral's underwater. And that's because Cape Canaveral, has anybody visited Cape Canaveral? I've never have, but you know, it's like right on the ocean, and it's like this far off the ocean. It's like right there. So you know, so that's close. And then Norfolk, Virginia, again, it's the largest naval base on the planet. It's worth trillions probably. And it may have to be moved, you know, because global warming is raising sea levels and causing flooding. We all know that Lower Manhattan, I don't know where my bearings are here now anymore, but Lower Manhattan, you know, we had Hurricane Sandy. So this is a story that's going to shock you, I promise. It's shock. I go to seminars in my Earth and Atmospheric Science building, and I swear, I hear some of these climate science people, you know, like glaciologists and stuff, and I sometimes feel like I'm in a science fiction movie, you know, like it's so incredible what's happening. And here's an example of that. So this guy came about, 3 years before Sandy, and Mayor Bloomberg had commissioned him to do a report of what would happen, what might happen to New York City at the end of a century with a 1 meter sea level rise. And his report, you know, so he came to Cornell and he gave this talk before Sandy, and he said, you know, the conclusions were 1 meter by itself wouldn't be a problem for New York City, but 1 meter elevation plus a storm surge on top of that will flood the subways and do all this damage. And Hurricane Sandy came at high tide, full moon, high tide, so it was 1 meter above its normal levels on average, and it flooded the subway. So this guy predicted the consequences of Sandy, okay? So he's a smart guy. He's not a crazy flake from his basement or something. So he came back. So Mayor, I just want to emphasize that because what he says a couple of years later, after Sandy, he came back, and Mayor Bloomberg said, okay, let's have a report on what we should do to prepare for this now. And there were a lot of authors, and some authors said we should build seawalls and we should do all this other stuff. And you know what his suggestion was? And this is the kind of thing I hear, like, not all the time, but like, it just shocked me. He goes, his suggestion was we move New York City. That was his suggestion. Like, that's, you know, and he goes, but he said, listen, it took 100 years, you know, with zoning to build up all the big skyscrapers. Since the early 1900s, all those buildings went up. You know, we just stopped zoning today. We don't let any new big buildings get built down in Lower Manhattan. We require them to build all the new buildings at the higher levels, higher